Okay, so it looked like we had a little sound glitch there when we switched from chapter 20 to 21, so we've restarted a new video. Chapter 21 was on aldehydes and ketones. We started out with a discussion of nomenclature. Here are some key suffixes. Al and carbaldehyde applying to aldehydes, one applying to ketones. Some common names for ketones that we learned. We also learned about acyl groups. We have a few common names there, like an acetyl group, a benzoyl group, for example. Nomenclature in general in this section of the class is most important in terms of being able to convert the names into structures, because you'll have some questions on the exam that instead of giving you structures will give you names of compounds, and you'll have to be able to convert those names into structures. So don't obsess about nomenclature, but make sure that you understand it well enough to convert names into structures. We talked about physical properties of these compounds. Aldehydes and ketones are comparable in that area because they cannot hydrogen bond to another molecule of themselves. They have intermediate boiling points, but because they can hydrogen bond to water, they do have some water solubility. We also quickly summarized the spectroscopic properties of aldehydes and ketones. And the key thing in terms of the IR is the CO stretch. And the key thing there was looking at alpha beta unsaturated aldehydes and ketones compared to normal aldehydes and ketones. And we told you that the CO stretch of an alpha beta unsaturated aldehyde or ketone shows up at a lower frequency, a lower wave number, than that of a normal aldehyde or ketone. And that was due to resonance. We explained it in class. It's an explanation that you should understand. Okay? Then NMR, in terms of the NMR spectroscopy, we learned that the aldehyde CH is highly deshielded. Okay, there are two reasons for that. So we have a chemical shift in the 9 to 10 ppm range for an aldehyde CH. Okay. And then in the C13, we reiterated this in chapter 22 as well. The carbonyl of an aldehyde or a ketone is more deshielded than the carbonyl of a carboxylic acid or its derivatives. Okay? So you should understand why that is. Rather than memorizing the numbers, understand why the aldehyde or ketone shows up at a higher chemical shift, more deshielded, more downfield than the carbonyl of carboxylic acids or derivatives. Okay? We discussed reactions we've already learned for preparing aldehydes and ketones. Okay? So for preparing aldehydes, we can oxidize primary alcohols. Okay, we need to use a special reagent there. We need to use PCC for that reaction. We can reduce esters and acid chlorides. Okay. We talked about that in chapter 20. We need the low temperature. We need either Dibol or lithium tritert-butoxy aluminum hydride. Okay. And then we can start from an alkyne and perform a hydroboration oxidation. Where we generate, if it's a terminal alkyne, we generate a terminal enol, and then that enol tautomerizes to give an aldehyde. So those are all reactions we learned previously. We also learned how to make ketones, or we summarized, discussed methods that we've already learned for making ketones. Oxidation of secondary alcohols will give us a ketone. We can also make ketones with acid chlorides and organocuprates. Okay, that was a reaction from chapter 20. We also have Friedel-Crafts acylation as a method of making ketones where we have an aromatic group. And then we also have alkyne hydration as a method of synthesizing ketones with mercury salt and water and sulfuric acid. Okay. And then we also learned ozonolysis. That can make aldehydes or ketones depending on the type of alkene that you're exposing to ozonolysis. So these are all reactions we learned in previous chapters that are important to remember if we need an aldehyde or a ketone for a synthesis problem. So the reactions of our aldehydes and ketones are nucleophilic additions. And there are two general mechanisms for nucleophilic addition. We have the normal one, where our strong nucleophile adds directly to our aldehyde or ketone. And then we have the acid catalyzed version, where we protonate the carbonyl oxygen first and then add the nucleophile. And so the first one we discussed was cyanohydrin formation. Okay, so when we are making a cyanohydrin, we use the combination of sodium cyanide and HCl, and we want to make sure we have excess sodium cyanide relative to the HCl. We talked about why that was in class. We also mentioned that your cyanohydrin can be cleaved with base to reform the aldehyde or ketone. You can add hydroxide and go back to the aldehyde or ketone. And we mentioned the utility of this process. Why would we do it? Usually it's not because we want the nitrile in our product. It's because that nitrile can be hydrolyzed to give a carboxylic acid. That's something we'll talk about on Friday at the end of chapter 22. Okay, so that was cyanohydrin formation. Then we learned about the Wittig reaction. The Wittig reaction was unique amongst our chapter 21 reactions because the oxygen of our aldehyde or ketone does not remain in the product. That happens in a couple of other cases. But in this case, we are forming a carbon-carbon sigma bond and a carbon-carbon pi bond in the reaction. Okay, so it is a carbon-carbon bond forming process. And so that makes the Wittig reaction one of our very useful reactions that we could call upon you to use in the context of a synthesis problem. Okay, we learned the mechanism. We form a four-membered intermediate, which is unusual because of its strain, but we learned that the phosphorus-oxygen bonds are strong, and the formation of a strong phosphorus-oxygen bond in each step of the Wittig reaction mechanism provides a thermodynamic driving force that causes the reaction to be favorable. Okay? We learned how to prepare Wittig reagents. We learned how to start with an alkyl halide and convert that alkyl halide into a Wittig reagent or an ylide, also known as an ylide. They're one and the same. A two-step process. We use triphenylphosphine followed by the use of a strong base. Okay. We also learned that when we're preparing an unsymmetrical alkene, we have two possible combinations of an aldehyde or a ketone plus a Wittig reagent. We want the less hindered Wittig reagent. Okay? So the less hindered Wittig reagent is better than the more hindered Wittig reagent. Okay? And then we also talked about stereochemistry. This was not in the book. We talked about it in class. It's important to know it featured on the quiz that we had on Tuesday. And we learned that the Z isomer is usually major. And we learned that E is favored with stabilized ylids. Okay. Whenever we have that double bond or that lone pair, whichever resonance structure of the ylid you're drawing, whenever we have that conjugated to either an alkene or a carbonyl, that's a stabilized ylid, and the E isomer is favored in that case. Okay? So Wittig reaction, very important, very useful for carbon-carbon bond forming processes. Okay? Then we learned about imines. We learned how to make imines. We react our aldehyde or ketone with a primary amine, and we add mild acid. We define that as having a pH range of 4 to 5. So we learned the mechanism of how imines are formed. It's important to be able to draw that mechanism. It's important to understand why we need acid, but why that acid should not be too strong. If it's too strong, you'll just protonate your primary amine and it won't function as a nucleophile. We learned that this is a reversible process. So if we take an imine and we add water, if we add aqueous acid to an imine, then we can go back to the aldehyde or ketone and the primary amine. And you should be able to draw the mechanism in either direction. We've had several mechanisms in this section of the class that you should be able to draw either in the forward or in the reverse direction. Okay. Then we had enamines. Enamines are made by reacting aldehydes or ketones with a secondary amine and mild acid. Okay. And the good news is the mechanism of forming an enamine is identical to that of forming an imine up until the final step. But there's no NH available to deprotonate in the final step of enamine formation. So you have to deprotonate from the alpha carbon to generate an enamine instead. And that reaction is also reversible, so you should know the mechanism forwards and backwards as well. Okay? Then we talked about making hydrates, about adding water to aldehydes or ketones. Okay? And we have two mechanisms for this process. One involving acid, one involving base. They're both catalytic in acid and base, so you should be able to draw those mechanisms. And then the other thing that you should be able to do with hydrates is to rank them according to their relative stability. In the vast majority of cases, hydrates are not favored in terms of the equilibrium. The aldehyde or the ketone is more stable. But we can rank them according to their relative stability. Some hydrates are more or less stable than others. And so that's a skill that you should have. Related to hydrates are acetals. In contrast to hydrates, with acetals, we're actually able to push the equilibrium using Le Chatelier's principle by removing the water. This also featured on the quiz because we talked about using an azeotrope with benzene, where water and benzene form a constant boiling mixture. That's the definition of azeotrope. And that's how we remove the water from the reaction, driving it to completion. And we use that special apparatus, the Dean-Stark trap, in order to do that. Toluene sulfonic acid is necessary for these reactions. We need a strong acid that dissolves in organic solvents. And then the mechanism, we should be able to draw the mechanism. It's reversible, so we should be able to draw it in the forward and the reverse direction. A key aspect of that mechanism is that the hemiacetal is the intermediate in that process. So we form an acetal, then a hemiacetal, and then the hemiacetal is converted into the acetal. Okay. If we want to hydrolyze an acetal, if we want to go backwards in the other direction, the hydrolysis would involve aqueous acid. We would want a lot of water presence. Okay. So we would use sulfuric acid and water. And you should be able to draw that mechanism, just the reverse of acetal formation. A couple more things with acetals. We learned that cyclic acetals are protecting groups for ketones and aldehydes. Okay, we don't form acetals from esters or carboxylic acid derivatives. We only form them from ketones and aldehydes. So we went over an example where we would have a molecule that had an ester and either an aldehyde or a ketone in it. We could protect the aldehyde or ketone as a cyclic acetal, perform a reaction on the ester, and then deprotect with acidic hydrolysis, restoring the aldehyde or ketone. So this is the second protecting group we've encountered in this section of the class, the first being the silyl ether that protects alcohols. And then finally, the last thing we learned is that we have cyclic hemiacetals that are stable. Most hemiacetals are not stable. They either get converted into acetals by Le Chatelier's principle or hydrolyzed to give aldehydes or ketones. But cyclic hemiacetals, the ones that have 5 or 6 members in their ring, are the most commonly existing form of carbohydrates, such as glucose. And so they are stable. They will exist in solution. You can also convert them into acetals, which are also components of carbohydrates. And that's something that we're going to learn later on in the class. All right, so that's it for chapter 21. We'll erase and go forward with chapter 22. And hopefully our sound will stay on this time, but if not, then we'll stop the video and restart with another one. Yeah, if we can erase quickly, hopefully it won't glitch. Okay, chapter 22 is on carboxylic acid derivatives, and the main reaction of our carboxylic acid derivatives, nucleophilic acyl substitution. Okay, so just like with chapter 21, we started chapter 22 with a nomenclature section. And the nomenclature of all of our carboxylic acid derivatives is closely related to the nomenclature of carboxylic acids themselves. And as I mentioned in chapter 21, it's most important to be able to convert the names into structures. The nomenclature is summarized in a table very nicely Table 22.2 gives you examples of the nomenclature of all the carboxylic acid derivatives. Physical properties. A key thing, a key aspect of our physical properties is that primary and secondary amides have higher boiling points than any of the other compounds in this section. Okay, these have NHs. They're able to hydrogen bond to each other, whereas tertiary amides cannot. Neither can any of our other carboxylic acid derivatives. So that's our key information in terms of physical properties. Spectroscopy. So we talked about IR spectroscopy, and the important thing to understand here is the relationship between the basicity of our Z group, right? We have our Z group in our carboxylic acid derivatives. The relationship between its basicity and the stretching frequency of the CO bond, okay? The more basic that Z group is, the lower that stretching frequency is. The less basic, the higher it is. And we explained that in terms of Hooke's law as well as resonance theory. Okay? And then NMR. I alluded to this in chapter 21, where it's important to know that why aldehydes and ketones appear at a higher chemical shift than carboxylic acid derivatives. And then another thing that we another comparison we made in this section is the position of the nitrile carbon in the C13 NMR versus an alkyne carbon, right? This is going to be downfield at a higher chemical shift. So those comparisons are important, okay? Nucleophilic acyl substitution. Our characteristic reaction that dominates this chapter. We already learned the mechanism of it back in chapter 20. The thing we focus on in this chapter is the relative reactivity, okay? So you need to understand the reasons. Understand the reasons for the relative reactivity of our different carboxylic acid derivatives. You need to understand why acid chlorides are the most reactive, followed by anhydrides, followed by carboxylic acids and esters, and then amides at the bottom, right? Related to the basicity of our Z group. And then remember we explained how that Z group and its leaving group ability, which is correlated to basicity, how that impacts both steps, both key steps of the nucleophilic acyl substitution mechanism, both the nucleophilic addition step and the elimination step, okay? All right, so we talked about several different types of reactions. We started with our most reactive derivatives, our acid chlorides, okay? And we talked about making esters from our acid chlorides, right? Reacting them with alcohols. So acid chlorides plus alcohols will give us esters. And we use pyridine as a base in this case. That pyridine is used to neutralize the HCl that is produced in the reaction, okay? We talked about reacting acid chlorides with carboxylates. That makes anhydrides. No base is required because our carboxylate is a negatively charged nucleophile, so we're not forming HCl in that case. And then we talked about acid chlorides reacting with amines, and we're making amides in those reactions. And we're using two equivalents of our amine. One is functioning as the nucleophile, the other is functioning as the base. Okay? All right. Then we went on to anhydrides. We didn't spend a whole lot of time on the reactions of anhydrides because they're very, very similar to acid chlorides. The only difference is we're using a carboxylate ion as our leaving group as opposed to chloride. So the same principles apply. We're reacting with alcohols. We use pyridine in that reaction. Esters are the products. We react with amines. We use two equivalents of the amine in that case. One is functioning as the nucleophile. The other is functioning as the base. Okay. And the most famous or infamous reaction with anhydrides was the one we showed you at the end of class on Tuesday, making heroin from morphine. Please do not try that at home. Okay, then today in class we started off with the reactions of carboxylic acids. We were able to convert carboxylic acids into all four of our carboxylic acid derivatives. But we have to pay attention to the acid-base chemistry. We have an acidic hydrogen in a carboxylic acid that complicates its reactivity. That hydrogen is not present in the carboxylic acid derivatives. So we can convert a carboxylic acid to an acid chloride. We're going to use thionyl chloride and pyridine. Remember, the book didn't mention the pyridine, but I told you it's essential. And we went over the mechanism of that in class. We can convert a carboxylic acid into an anhydride. We're not using that silly reaction that was in the book just for making the cyclic anhydrides. Here we're using a carboxylate, the conjugate base of our carboxylic acid, and an acid chloride. That's how we're going to make our anhydrides. Okay. Then we talked about converting carboxylic acids into esters. That is the Fischer esterification, where we're using an alcohol and sulfuric acid as a catalyst. That's an equilibrium reaction, remember. So it is a reversible process. And then carboxylic acids to amides. We cannot simply mix a carboxylic acid and an amine. We'll just have an acid-base reaction to give a salt. But if we use DCC, dicyclohexyl carbodiimide, we're able to convert the carboxylic acid OH into a good leaving group, allowing that nucleophilic acyl substitution to take place. Remember that mechanism. We have an intramolecular proton transfer that works because it has a six-membered cyclic transition state. Okay? So those are our reactions of carboxylic acids. So next we discussed reactions of esters. And both of our reactions of esters we discussed resulted in converting them into carboxylic acids. We had the acidic hydrolysis. The acidic hydrolysis is simply the reverse of the Fischer esterification. It's a reversible equilibrium process. This was the one that explains why we don't use esters in perfumes or colognes, even though they do smell good. And then we had our basic hydrolysis, which we also called saponification. and the saponification reaction was irreversible, we formed a carboxylate as the product, not a carboxylic acid. And the last step in that mechanism was highly favorable, and what is what makes the whole process irreversible, and also makes it consume an equivalent of base as opposed to being catalytic in acid. Okay, and we talked about how that reaction is used to make soap. Amides, same types of reactions. Amides are our most stable carboxylic acid derivatives. So we're only able to convert them into carboxylic acids. We cannot convert them into esters or other derivatives. So we have an acidic hydrolysis reaction. And we went over that today in class. Same mechanism as acidic ester hydrolysis, with the exception of the final step where we're using the amine as a base, as opposed to using the conjugate base of our acid, okay? And so that meant that we consumed an entire equivalent of our acid. This reaction was not catalytic in acid, okay? So that was a difference between hydrolysis of amides and acidic hydrolysis of esters, okay? And then on Friday in class, we're going to start out with the basic hydrolysis of amides. And what we'll encounter in that reaction is something unique. We will encounter a highly unfavorable step, a step where the equilibrium strongly favors the reactants. But then we're going to have a very highly favorable and irreversible step after that that allows us to drive the reaction through the unfavorable step. And that's what we'll start with in class on Friday. Then we're going to talk about penicillin. Penicillin is one of my favorite molecules, and it has a special amide that is more reactive than other amides. And we'll explain why that is the case in class on Friday. So you should understand the mode of action of penicillin and understand why it is more reactive than most amides. Okay? Then we'll talk about acyl phosphates. So we'll talk about our biochemically relevant carboxylic acid derivatives. One of those is the acyl phosphate. So acyl phosphates are comparable to anhydrides. They're a little bit less reactive than anhydrides. And so to get them to react with alcohols and amines in the body, we usually add a magnesium cation. That magnesium cation, of course, is going to be present in the active site of the enzyme where these reactions take place. We'll talk about the role of that magnesium cation in class. And then we'll talk about the preparation. So acyl phosphates are prepared from carboxylates, right? Conjugate bases of carboxylic acids and ATP. These species react together to make our acyl phosphates. And then we'll talk about their reactions. Acyl phosphates plus amines is how we generate amides in biochemistry. We also react our acyl phosphates with thiols to make thioesters. Okay. And then, of course, we'll talk about thioesters. Thioesters, since you can make thioesters from acyl phosphates, that implies that they're less reactive than acyl phosphates, and that is true. Thioesters are also used in biochemistry, so they're produced from acyl phosphates, and they're usually converted into esters. So you react them with alcohols, and that generates esters. You could also react them with amines to generate amides. The example we'll talk about in class is one where we make an ester. Okay? Then we conclude with nitriles. Nitriles are the molecules in this chapter that don't have a carbonyl group, but they're analogous to our carboxylic acid derivatives because we have 3 bonds between the carbon of a nitrile and a heteroatom, nitrogen in this case. Okay. First thing to know is how we prepare nitriles. We can make them with cyanohydrins. We talked about that in chapter 20. But we can also do SN2 reactions with cyanide as a nucleophile. Okay, so alkyl halide converted into a nitrile, an SN2 reaction with cyanide. So that's one aspect of nitriles that's important. And then there are 3 reactions of nitriles that we're going to learn on Friday that are important to understand. The first one is hydrolysis. We mentioned this in chapter 20. We can hydrolyze a nitrile to generate a carboxylic acid. We're going to need either acid or base for that reaction. We'll learn those mechanisms in class on Friday. We can reduce a nitrile, and that gives us a primary amine if we use lithium aluminum hydride. We can reduce a nitrile to give an aldehyde, a new way of making an aldehyde, and that uses dibol as the reducing agent. Okay, so another interesting reaction that we'll learn. And then we can add organolithiums or Grignard reagents, and that reaction affords ketones. Okay, so we're going to talk about nitrile chemistry at the end of the chapter. You might be tempted to ignore it because nitriles are not carboxylic acid derivatives. I would strongly suggest not ignoring it because the nitrile is a very versatile functional group. We can convert it into a carboxylic acid, a primary amine, an aldehyde, or a ketone. So in the context of a synthesis problem, nitrile chemistry could be very valuable to you because of the fact that you can transform that functional group into a lot of different functional groups. So that's our summary of the key topics from chapters 20 to 22. Enjoy your studying and good luck on the exam.